Here is the structure of ethanol. It is CH3CH2OH. The black atom represents carbon. The white atom here represents hydrogens. There you see 3 of them. And the red atom here represents oxygen. There you see a hydrogen attached to it. So this molecule is the covalent structure of ethanol. Once again, CH3CH2OH. And you can see here in the molecule we have all single bonds around it. Now I'm going to do something here. I'm going to break this molecule apart. I'm going to remove this bond here. And I'm going to take this oxygen atom. I'm going to attach it right to this carbon atom here. And I'm going to take this carbon atom and I'm going to put it at the end. I have this, I'll attach it here. And now I have not added any atoms. I have not subtracted any atoms. All I've done is remove that oxygen at the end and put it at the center, that red colored ball. And now I have an entirely new molecule. And this new molecule is called dimethyl ether. Dimethyl ether. So ethanol and dimethyl ether are known as isomers, which means that it's still CH and O, and that's what the empirical formula is, but the arrangement of the atoms is entirely different. So now in ethanol you had the oxygen at the end. In dimethyl ether, or dimethyl ether, the oxygen is right at the middle. So the question we want to ask ourselves is, what is the difference between ethanol and dimethyl ether? Because obviously the difference is in terms of the arrangement of the atoms, but how does that influence the physical properties, melting point, boiling point, etc.? This data, the melting point of ethanol is actually minus 114.1 degrees. Compare that with the melting point of dimethyl ether, and it's minus 141 degrees C. If you look at the boiling point of ethanol is 78.37 degrees Celsius. And look at the boiling point of dimethyl ether, minus 24 degrees C. So that is a resounding difference. It's again 2 carbons, 6 hydrogens, and 1 oxygen. They are arranged differently. In one arrangement, the boiling point is minus 24 degrees, and in another arrangement, the boiling point is 78.37 degrees. And then the vapor pressure exerted at room temperature, 25 degrees C, is substantially less for ethanol than it is for dimethyl ether. So the point being is that these two molecules exhibit very differing and very profound intermolecular forces. The strength of intermolecular forces are labeled in this pyramid from the weakest to the strongest. So let's go over these. First of all, we have almost the universal intermolecular force, and that is London dispersion forces. London dispersion forces exist everywhere. They're universal. So a typical question, what type of forces exist between molecules? London dispersion forces will always exist. And this has to do with the electron cloud and its circulation around the nucleus. Since all molecules are going to have an electron cloud that circulates around it, some electron clouds will interact preferentially with some molecules and some will not. Because the cloud is constantly moving, there is going to be a partial negative and a partial positive force that allows these intermolecular forces to very weakly interact with one another. So the point being is that London dispersion forces are universal. They're found everywhere, but they're substantially weak. Now, on the next level up, we have dipole-dipole forces. This occurs when you have polar compounds. So remember, polar compounds versus nonpolar compounds. London dispersion forces would exist between nonpolar compounds. It would also exist between polar compounds because they exist everywhere. This is a universal force. It's very weak. Now, moving up the chain here, dipole-dipole forces only exist if your compound is polar. Take a look at these two compounds here. One of them is formaldehyde, and the other one is dimethylbromine. And what is the type of interaction a formaldehyde molecule will make with another formaldehyde molecule? Will they even interact at all? So the answer has to do with polarity. So if you look at the electronegativity scales, oxygen and carbon, in this bond, this covalent bond actually is not shared equally. This oxygen atom has more electronegativity than the carbon. So what we do is, to illustrate that, this formaldehyde molecule has a net dipole moment. This oxygen is pulling electron density towards itself. And when it does so, it makes this carbon a partial positive charge. This is the symbol for delta. And this oxygen has a partial negative charge. So it's important to recognize that within the formaldehyde molecule, you have a region of the molecule that has a partial positive charge, that's this carbon, and you have a region of the molecule that has a partial negative charge, and that is this oxygen. The key word here is partial. Okay, this is not a total positive charge or a total negative charge. This oxygen region of the molecule is going to be more negative or partially negative. Likewise, this carbon region of the molecule will be more positive or partially positive. And we know that partial positives will like to interact with partial negatives. So this partial negative will interact with a partial positive of another molecule. It could be another partial positive of a formaldehyde, or it could be another partial positive of another molecule itself. So polar molecules will interact with one another through their dipole moments. So, for example, if formaldehyde were to interact with another molecule of formaldehyde, it would interact possibly with the partial positive of the carbon, or it could interact with the partial positive of the hydrogen. I'll have it interact with the partial positive region of another formaldehyde molecule. And like that, this can go on and on. This partial negative can interact with another partial positive. So the partial positives will interact with the partial negatives. And in a polar compound, you get that type of very nice interaction. It's much stronger than van der Waals forces. Formaldehyde actually has what's called a net dipole moment. Same situation arises with methyl bromine. So here we take carbon. Carbon loves 4, so we attach it with 3 hydrogens and 1 bromine. sp3 carbons like to be tetrahedral, and this is a tetrahedral molecule. It's also polar, because what does the bromine do? The electronegative bromine is going to pull electron density towards itself. So this is not a single bond that's shared equally, just like this is not a double bond that's shared equally. This bromine, by virtue of its electronegativity, is going to pull electron density towards itself, and that's going to make it partial negative. And since this becomes partial negative, this becomes partial positive. What would a partial negative like to interact with? It would like to interact with a partial positive. Now it could interact with a partial positive from a totally different molecule. It could also interact with the partial positive of itself, another molecule of methyl bromine. So here I'll have this partial negative methyl bromine localized within the bromine. That partial positive, I'll have it interact with the partial positive carbon of another methyl bromine. You have a partial positive with a partial negative interaction. So that's a strong interaction, definitely much stronger than van der Waals forces, which results in, or also called London dispersion forces, which, as we've mentioned before, results just as a very weak intermolecular interaction as the electron clouds are constantly moving. We look at the next stage of strength between intermolecular forces. We have to go with hydrogen bonding. Hydrogen bonding is a big one. It's huge. It's very important in the bonding of water to itself. It's very important in the three-dimensional structures of proteins. It's very important in the three-dimensional structures of sugars when they join together, or complex carbohydrates. And hydrogen bonding is crucial. Some people will even go so far as to state hydrogen bonding is very essential to life itself. And it exists between 3 atoms. So hydrogen bonding, so there has to be a hydrogen here. So we'll call this molecule 1. And hydrogen bond can occur between molecule 1 and itself. Water can hydrogen bond to itself, henceforth why it has such a high heat of vaporization or boiling point. Or it could hydrogen bond with a totally different molecule. So the first situation, or the first special atom, would be with a nitrogen. So we have our molecule here, that whatever the end of that molecule, it could be 1 atom, 2 atoms, or several atoms long. But within that molecule, there's going to be an NH. Okay? Now, it could be an NH2, it could be an NH3, it could be any type, but there has to be an NH here. So if that NH, this nitrogen is going to be partial negative, and this hydrogen is going to be partial positive, what happens is that this nitrogen on molecule 1 can form an attractive, so these are all attractive forces, with the hydrogen that's attached to another molecule. Okay? And that could be with another hydrogen attached to an H. It could be with a hydrogen that's attached to an O, or it can be with a hydrogen attached to an F. So that is, in essence, what a hydrogen bond is. So all of these are attractive forces. Notice the fluorine as part of molecule 1 or a different molecule, or the nitrogen as part of the same molecule or a different molecule, or the hydrogen, or the oxygen as part of the same molecule or a totally different molecule. Going to pull, okay, they're going to pull this way. These hydrogens partial positive. That will interact with the partial negative of the nitrogen. So interact with the partial of an oxygen. All of these are attractive forces. And molecule 1 will have that partial negative from the oxygen. Hydrogen becomes partial positive. And then finally, the third type of atom that can facilitate a hydrogen bond is going to be fluorine. So if we have, now fluorine, we don't see that a lot in biochemistry, so we'll probably may see that in general chemistry. Fluorine, this is going to be a partial negative. Fluorine is one of the more electronegative elements in the periodic table. And fluorine is going to pull electron density this way. It's going to be partial negative, and it's going to have attraction towards the partial positive of a hydrogen on another molecule attached to an oxygen. A partial attraction with a hydrogen attached to another nitrogen. Have a positive attractive with a hydrogen attached to another fluorine. So remember, with hydrogen bonds as a part of an intermolecular force, could hydrogen bond to itself. And that's what we see with water. We see a very beautiful hydrogen bonding lattice when it comes to water. Water can hydrogen bond to itself. You can see here in our lecture notes the extensive hydrogen bonding network that occurs in a water molecule. This is why it takes about 6,000 joules of energy to break 1 mole of ice. 1 mole of ice, 1 mole of water is 18 grams, so roughly 6,000 joules it takes of energy to break apart 1 mole or 18 grams of ice. You can see that these hydrogen bonds are all over the place. This is one of the reasons why molecules have such high boiling points, is because it takes a lot of energy to break apart this hydrogen bonded network. Longest interaction between molecules is ionic interactions. We won't go over that so much in this class, but this is truly a lattice because this is a complete and total electron transfer. Think of sodium chloride, or think of potassium chloride, think of calcium chloride. These are generally called salts. You get lattice-like structures or salts, and these can have different arrangements, such as a cuboidal shape or hexagonal shape. Really, kind of like your crystals, a very, very organized, kind of like a brick in a brick house. These are going to be very structured and very organized because this is a complete transfer of electrons. These are interactions that are partial. A partial positive interacting with a partial negative. This is especially strong because it's very unique. It's a special category. And these dipole-dipole forces are also strong. The hydrogen bonding is a little bit stronger. It imparts more strength. So hydrogen bonding is a special category of dipole-dipole forces. This is hydrogen bonds are a little stronger than the generic dipole-dipole forces that would exist between polar compounds. That I did not mention, or is not in that triangle, is ion-dipole forces, and they exist when an ion interacts, a completely charged ion interacts with a partial negative or a partial positive of another molecule. So molecule 1 would be polar, with a partial positive or a partial negative end. And then the second interacting component is an ion. So this is a complete charge. So you have a complete charge interacting with a partial charge, and that is also an attractive force. It's between an ion and a polar molecule, and this is the reason why we have our solubility table. If you remember your solubility table from Chemistry 1, think of sodium chloride or your sodium nitrates, or all those things. They actually dissolve in water. Dissolve in water very well because water is a polar compound, can exhibit hydrogen bond, but really the partial negative charges on the water molecule and the partial positive charges on the water molecule will interact with the complete positive charge and the complete negative charge of an ionic compound. So this is called solvation. Sodium chloride breaks up or dissociates in water. That's why sodium nitrate dissociates into water. This ion-dipole force is responsible for what we call solvation. The C solvation here. So take a sodium ion from sodium chloride. The sodium ion will interact with the partial negative of the water molecule, and the magnesium ion will interact with the partial negative of the water molecule. And you notice how the ion is sort of entrapped with the partial polarities of the water molecules. So in this particular case, the sodium ion is solvated by not 1, not 2, not 3, not 4, not 5, but 6 water molecules, specifically that oxygen, because oxygen is partial negative, the partial negative properties in the water molecule. Size plays a role in this. So magnesium ion that has lost 2 electrons will have a positive charge. Plus 2 is more positive than plus 1. So that plus 2 will interact strongly with the partial negative of the water molecule. So our physical properties here between ethanol and dimethyl ether. Want to bring your attention to the boiling point. The boiling point at 78 degrees is about 8 degrees higher than the boiling point of dimethyl ether. What do you think is happening here that results in almost a 90-degree increase in the boiling point between 2 molecules that are composed of exactly the same atoms? Well, looking at ethanol and looking at dimethyl ether, what type of intermolecular forces binds ethanol molecules together? The answer is hydrogen bonding here. Okay, so hydrogen bonding would exist in molecules as polar or dipole-dipole actions with the polar compound of dimethyl ether. So hydrogen bonding is much stronger than dipole-dipole interaction. Methyl ether only has polar interactions, and polar interactions or dipole-dipole moments are not as strong. So essentially dimethyl ether exists as a gas at room temperature. It easily vaporizes. And really it tells you how in the pyramid of strength, the hydrogen bonding is a much stronger force than dipole-dipole interactions. You can see that here just by looking at the boiling points. And bonding, one more time, is with ROH, RNH, F, okay, with another molecule, O, nitrogen, here for the fluorine. Vapor pressure is very low for ethanol, and the vapor pressure is very high for dimethyl ether. That has to do with what the definition of vapor pressure is. You see, ethanol really doesn't want to form as a vapor. And this is at room temperature because your vapor pressure changes as a function of temperature. It increases as you increase the temperature, you increase the vapor pressure. The pressure that's exerted by ethanol is very low because ethanol tends not to form as a vapor. The hydrogen bonds keep it as a liquid or keep it as sort of that phase as a state of matter, whereas dimethyl ether can easily go into the vapor phase because it can easily overcome those dipole-dipole interactions. Let's go over the dipole-dipole interactions of dimethyl ether. These oxygen, the center, it's going to sec electron density towards it, making it partial negative. And the same thing on the other end of the molecule. It's going to be partial negative because oxygen is sucking electron density towards itself, and it's making these carbons partial positive. But there's no hydrogen bonding here because you don't see an O bound with an H, you don't see an N bound by an H, you don't see a fluorine anywhere near the molecule. So there's no potential for hydrogen bonding. These are all interactions. Okay, these are not covalent sharing or complete transfer of electrons as you would expect for ionic compounds, which are more salts and more crystalline-like. This is just an attraction between molecules, and that's one of the reasons why you have such a substantial difference in melting point, boiling point, and vapor pressure. It's 100 times more vapor pressure that it exerts than ethanol, because this can easily go into the vapor state. This cannot go so much into the vapor state unless you break apart the hydrogen bonding network. We see this intermolecular attraction really manifest itself in some of these compounds. You'll study more of these in organic chemistry. Each of these points, these ends, represents a carbon atom. So this would be a carbon with hydrogen, this would be a carbon with hydrogen, this would be a carbon with hydrogen, and that would be a carbon with hydrogen. Same thing here and same thing there. Just want to bring your attention to the type of intermolecular interaction. So this nitrogen is electronegative. It's going to take electron density towards itself and be partial negative. So that partial negative, the nitrogen, will interact with the partial positive of another molecule. As a result, you have dipole-dipole interactions, polar-polar interactions, and that gives you a boiling point of 36 degrees. Contrast that with N-butylamine. You see that NH, you not only have not one H, but you have two H's, so that NH can form a hydrogen bond. That nitrogen can form a hydrogen bond with a hydrogen of another N-butylamine molecule. A strong dipole-dipole moment, a special category of dipole-dipole moments, is hydrogen bonding. You can see an increase in the boiling. That has a complete positive and complete negative charge. It's ionic, and that has a very high boiling point. These are going to be your salts. These are going to be like your crystalline. It's going to be a complete lattice structure, guys. All right. So methyl propionate, that oxygen and that oxygen will be partial negative, and that will interact with the partial positive of other molecules, another molecule of methyl propionate, or another partial positive of a separate entity. And you have dipole-dipole interactions. Pretty strong here, 80 degrees is its boiling point. Butyric acid, now you introduce that H, and that can be a source of a hydrogen bond. So this H will hydrogen bond with another oxygen. Oxygen can hydrogen bond with the hydrogen of another butyric acid, and that hydrogen bonding gives it a boiling point of 163 degrees. And then sodium butanate. Okay, all of these are carboxylic acid derivatives, and if you had that O minus, fully negative, interacting with a fully positive sodium ion, so it's a complete ionic interaction, very high boiling point. Again, because this is not a partial interaction, it's a complete charge interacting with a complete positive charge. If you look further down, okay, these are all your typical organic solvents, and you notice pentane, okay, hydrocarbons, boiling point 36.3 degrees, no oxygens, no hydrogen, no oxygens, no nitrogens, no fluorines, no chance to hydrogen bond with itself. Once you start adding that OH, now potential for a hydrogen bond, the boiling point increases. You need to add a lot more temperature to disrupt those hydrogen bonds. And whether you add hydrogen bonds with an OH, or you can add another OH here. Now here you have more carbons, and you have a more branched structure, so that branching, you notice the CH3 is branched, where this is a straight chain. That branching actually modulates your boiling point just a little bit. But usually more carbons, higher the boiling point, the addition of OH or NH or even a fluorine in there will also skyrocket the boiling point. Some practice problems here. Which of the following species are capable of forming hydrogen bonds amongst themselves? S, C6H6, or C3H3OH. This is hydrogen sulfide. Okay, remember hydrogen bonds, NH, OH, or fluorine there, so really no hydrogen bonding potential. C6H6, okay, look for an OH in the molecule or an NH in the molecule or a fluorine. Not there, no bonding. This would probably have dispersion forces. There's nothing electronegative here if it were to interact with itself. This would probably have dipole-dipole interactions. The sulfur will pull electron density. It's sufficiently electronegative. And methanol, CH3OH, would exhibit hydrogen bonding. That OH can form a hydrogen bond with another H with this oxygen. This hydrogen can form a hydrogen bond with another oxygen of a methanol. One down here. Which of the following can form hydrogen bond with water? And now look here for oxygens, nitrogens, or fluorines in the molecule. And this can form a hydrogen bond because that oxygen can form a hydrogen bond with the water molecule, H2O. This CH4 cannot do anything. There's nothing electronegative about it. It's a nonpolar molecule. Only London dispersion forces exist in that. F2 will not hydrogen bond with water because F2 is a nonpolar molecule. The electronegativities cancel with one another, so we would expect no interaction between polar water and fluorine. OOH, this is acetic acid. We would expect it to form hydrogen bonds with water. Sodium ion will not form a hydrogen bond with water. It will actually solvate, and this would be an ion-dipole interaction. So it will interact, but it's not a hydrogen bonding interaction. It's an ion-dipole interaction. Hydrogen bonding interaction, this interaction because this is nonpolar, this is polar. Interaction because this is nonpolar and this is polar. There will be a hydrogen bonding interaction because this is polar and this is polar. And specific hydrogen bonds occurs between this oxygen of dimethyl ether and this hydrogen, one of the hydrogens of the water molecule.